Hello and welcome to Controllers Tech. In this video from the Mongoose Networking Library series, we will learn how to limit the network functionality to a pre-allocated memory pool. This approach ensures that the network memory usage stays within a predefined limit, so you always have enough RAM available for other important operations in your system. We will also use the real-time graphs created in the previous video to monitor the live memory usage and the free memory available from the allocated memory pool. Before we start working on the project, let us first take a quick look at the main features of the Mongoose networking library. Mongoose is a TCP/IP network stack that comes with an embedded web server, an MQTT client, built-in TLS support, and firmware update functionality. Mongoose is used by hundreds of companies, both big and small, ranging from one-person freelancers to large multinational companies such as Bosch, Siemens, Google, and Samsung. NASA even uses Mongoose on the International Space Station, and you should use it too. With Mongoose, you can quickly create professional web-based device dashboards without any prior knowledge of web development, and you can easily connect your device to cloud services like AWS IoT or your own private server. Let us now create a project using the Mongoose dashboard. Click on New, and select Create a new C++ project. Now choose the folder where this new project will be created on your system. Next, select the development board. I am going to use the STM32H745 Discovery board. Choose the build environment as Cube IDE, and for simplicity, keep the RTOS option set to bare metal. Let us select the LED toggle dashboard, so we already have a basic example to start with. The basic dashboard is now ready, and we will add more elements according to our requirements. I am creating one more container, and inside this container, I will add two graphs, one to display the current memory usage, and another to display the free memory available. These graphs will show data for the last 30 seconds, and they will update every 25 milliseconds to provide near real-time information. I am going to allocate 40 kilobytes of RAM for networking purposes, so let us change the y-axis scale to 40,000. The same configuration will also be applied to the second graph that shows the free memory. Along with the LED control panel, I am going to add a gauge that displays the number of active connections, and this value will also update in real time. Let us now assign the ticks for the gauge. I am setting the range from 0 to 24, with ticks at every 4 connections. Alright, our dashboard design is complete, so now we will move on to creating the REST API endpoints for these elements. The LED endpoint is already created, and it has two attributes, one for each LED. The data type for these attributes is Boolean, so the button will return either true or false. Now let us create a new endpoint for the statistics. The first attribute of this endpoint will fetch the memory currently used from the allocated pool, the second attribute will fetch the free memory, and the third attribute will fetch the number of active connections. All of these attributes will use the integer data type. Set the stats endpoint to read-only, since the user interface will only read data from the MCU and will not write anything back. Now go to page content and assign the created endpoints to their respective graphs and gauge. We will use WebSocket to update the statistics, so enable WebSocket in the Settings tab. Also make sure to set the auto-update interval to 1 second. This enables the heartbeat mechanism, which refreshes the data on the page every second. That is all the configuration we need for now, so go ahead and generate the project. Now open the project folder, and here you can see the complete Cube IDE project generated by the Mongoose wizard. We will now import this project into Cube IDE. Open Cube IDE, click on Import Project, browse to the project folder, and then click Open to import the generated project. The project has been successfully imported, and this is the main file of the project. Before we start making any changes, let us first test the generated project to make sure everything is working as expected. Open the serial terminal so we can view the runtime logs. I am now going to connect the Ethernet cable to the board. The library has been initialized successfully, and we have received an IP address from the DHCP server. Let us copy this IP address and paste it into the web browser. The web UI dashboard has loaded correctly, and everything is working fine up to this point. To allocate a dedicated memory pool for networking, we will use a custom memory allocator with a predefined block of memory. There are many available memory allocator implementations, and some of the popular ones include FreeRTOS Heap 4 and Heap 5. I tried using Heap 4 for this test, but it required several FreeRTOS related header files and dependencies. Because of that, I decided to use another allocator called O1heap. O1heap is a very fast memory allocator designed for hard real-time and high-integrity embedded systems. To use the O1heap implementation, we only need to copy its source file and header file into our project. So, copy the raw code from GitHub, create new source and header files in the appropriate folders, and paste the raw code into those files. Build the project once to make sure there are no compilation errors at this stage. Alright, now open the Mongoose documentation, go to the user guide, and then navigate to build options. Mongoose allocates memory at runtime using the mgcalloc and mgfree functions. It also allows users to provide a custom implementation of these functions, so you can control how memory is allocated and freed. To enable custom allocation, we need to define mg-enable custom calloc in the Mongoose configuration file and set it to 1. After defining this option, if you build the project again, the compiler will show an error. This error is related to the mgcalloc function, because the default implementation is no longer available. At this point, we need to define these functions ourselves. You can find the default implementations of mgcalloc and mgfree inside the mongoose.c file. Let us copy these two functions from there and paste them into the main file. For now, I am leaving these functions empty, but if we build the project at this stage, it should compile successfully. This confirms that the compiler can now detect the custom implementations of these functions. Inside these functions, we will use the O1heap allocation and free logic, but before doing that, we need to initialize the heap properly. Let us start by including the O1heap.h header file. Next, define how much memory we want to allocate for networking. I am allocating 40 kilobytes of memory here. Create a buffer that represents this memory block, and make sure it is aligned according to the O1heap alignment rules. Now create an O1heap instance, which will be used throughout the code for memory allocation. Next, create a function to initialize the O1heap. Inside this function, call O1heap init to initialize the memory pool. The base address will be the buffer we created earlier, and the size will be the total size of that buffer. This function returns a pointer to the initialized memory fragment, and if it returns null, it means the initialization has failed. In that case, you can call the error handler to handle the failure. Inside the mgcalloc function, we will first calculate the total memory size required. Then we will call O1heap allocate to allocate the requested memory from the pool. If the allocation is successful, we will initialize the allocated memory to 0. Similarly, inside the mg_free function, we will call O1heap free to release the allocated memory back to the pool. Now we will move on to writing the getter and setter functions that were generated in the Mongoose glue source file. Let us start with the getter function for the stats. First, change the name of this function to avoid any conflict with the default generated function. Inside this function, we will call O1heap getDiagnostics to read the memory diagnostic information and store it in a diagnostics structure. This structure provides useful details such as the total memory capacity, allocated memory, and other related information. Next, store the allocated memory value in the RAM-occupied element of the stats structure. In a similar way, calculate the free memory and store it in the RAM-free element of the stats structure. The information about the number of active connections will be fetched from the Mongoose MG connection structure. This value will then be stored in the num connections element of the stats structure. Next, we will create a custom setter function for the LEDs. However, before we can control the LEDs, we need to configure the corresponding PO pins in CubeMX. Let us open STM32 Cube and load this project into it. While the project is loading, let us quickly review the hardware connections. This is the pinout of the STM32H745 Discovery board. I am going to connect the LEDs to pins PI8 and P6. Now go back to CubeMX, search for these pins, and configure both of them as output pins. Since this is a dual-core development board, we also need to assign these pins to a specific core. Open the PO configuration and change the pin context assignment to Cortex M7. That is all the configuration required in CubeMX, so let us generate the project now. Inside the LED setter function, write the logic to set the LED states based on the values present in the LED's structure. Our custom getter and setter functions are now ready, so the next step is to register them using an HTTP handler. Let us go back to the Mongoose documentation and open the section on WebSocket updates under the Mongoose wizard. Here, you can find an example showing how to register HTTP handlers along with a WebSocket reporter. Copy this HTTP handler function and paste it after the Mongoose initialization code. The first parameter of this function is the endpoint name, the second parameter is the getter function for that endpoint, and the third parameter is the setter function. After registering the HTTP handlers, we will call the WebSocket reporter function to send data to the graphs. This function will push the stats data every 100 milliseconds, allowing the graphs to update in real time. Alright, now let us build and flash this project onto the board. Open the serial monitor to observe the runtime logs. According to the logs, there appears to be an issue while allocating memory from the heap. To debug this, we need to check line 316 inside the O1heap allocate function. This is the point where the O1heap allocate function is being called. Here is line 316, and based on this line, we can see that the O1heap handle is null, which means the heap was never created in the first place. Now that I look back at the code, I realize that I never initialized the heap in the main function. So let us fix this by initializing the heap inside the main function, and make sure it is done before the peripheral initialization starts. There is one more issue in the project that we need to address. We also need to define a custom getter function for the LEDs. Just like the LED setter function, create a new custom LED getter function. Inside this function, read the PO pin state and store the values in the corresponding elements of the LED's structure. Now, inside the HTTP handler registration function, define both the getter and setter functions for the LED structure. There is still an error here. I forgot to change the name of the LED getter function, which is causing a conflict. Alright, let us build and flash the project to the board again. This time, everything has been initialized correctly, and the same IP address has been assigned by the DHCP server. Let us open the browser and check the live updates. The memory graphs are now displaying data correctly. The memory usage is around 28 kilobytes, and the free memory is approximately 12 kilobytes. The number of active connections is currently 6, and this includes the HTTP and HTTPS listeners, the WebSocket connection, the Heartbeat API, and other internal connections. Let us test the LED control once. The LEDs are responding correctly to the buttons on the WebUI dashboard. Now let us add a few more connections and observe how the memory usage changes as new browser tabs are opened. You can see that the memory usage increases to about 35 kilobytes, and the free memory drops to around 5 kilobytes. Let us repeat this once again. The memory usage has now increased to 37 kilobytes, and the free memory has dropped to about 3 kilobytes. Let us keep adding new tabs until the memory pool is fully exhausted. At this point, the logs are still showing only the heartbeat messages, so the system is operating normally. Now the free memory is down to just 1 kilobyte, and in the logs you can see that out-of-memory messages have started appearing. After this point, if we add more connections, the server will no longer accept them, because there is no memory left in the allocated pool. If we close the active connections, the memory usage starts decreasing, and the free memory begins to increase again. You can also see that the number of active connections is going down at the same time. So this is how we can limit networking activity using fixed memory constraints. By allocating a predefined amount of memory for networking, all network-related operations are restricted within that memory limit. That brings us to the end of this video. You can download the complete project from the link provided in the description of this video. Feel free to leave a comment if you have any questions or doubts. Keep watching, and have a nice day ahead.